Hello everyone, this is Tony Adamson of Vibrasonic Control, and today I'd like to talk a little bit about vibration isolators and the effect of deflection and what that does to isolation and how it affects equipment and your selection of what isolators you want to use. So what I have here in front of me is a fan. It has an imbalance, which we put a bolt in here so it can throw it out of balance, and it's also got a variable frequency drive so that we can adjust the RPM of the equipment. So it's very out of balance. For a small fan like this, it's a terrible piece of equipment, but it's great for our demonstration. So if I turn it on, and I don't want to leave it on too long because it creates quite a terrible noise and annoying everyone in the building. And that's because it's way out of balance and it's sitting flat on this table and it's got no isolation whatsoever. So what do we do about that? We've got to get some isolators, and we've got to isolate this piece of equipment. So step one, we're going to try some neoprene waffle pad, or rubber waffle pad. You will see this quite a bit out there. It's quite often used under pumps or equipment like that. It can be effective for equipment when it's somewhere not critical or slab on grade. And it doesn't have a whole lot of deflection. It's usually rated to about maybe a 20th of an inch. And in this case, they're quite a bit larger than what I need for this fan, so we're not even going to get that. We're getting very, very little, quite honestly. So I put it on there. Now we've got it isolated. It's got the rubber between the piece of equipment and my table, so we're good to go. Let's see how it helps us out. As you can see, it didn't really help too much. In fact, it kind of bounced around more than it did before. That's because we're really not getting any deflection. And that deflection is what gives us vibration isolation efficiency. The greater the deflection, the better our efficiency. And you'll see those numbers sometimes. Isolation efficiency, that is a percentage, and that percentage is how much of that energy is being taken out and doesn't get into your structure. So if you have a vibration isolation efficiency of 90%, then only 10% is getting down into your structure. It's taking out that 90. In the case of these neoprene pads, I would say it's about 0. So we move to something a little bit more robust, something with greater deflection. That's neoprene mount. It's still neoprene or rubber, and it's thicker though, so now it's got some deflection. It will squash down under load. So if we move these out here, we should have some increase in performance, some better isolation efficiency. What you do see when I put this down on here, it still doesn't deflect much. Quite honestly, they're underloaded, and you're not going to get much deflection, not very noticeable anyway. Still more than the pads, but it's just not a lot. So let's see what happens when we use our neoprene mounts. As you can see, it still wasn't that effective. It was better than the pads, but I think this one here tried to sneak away. It's letting the whole thing bounce around, and quite quickly you'll find that resonant frequency because we're not getting a lot of deflection here. So it's, again, not really adequate, particularly with this noisy fan, and if we turn down that RPM, it's going to even be worse. So it's not really a great selection for our problem that we have here right now. That's when we move into something with greater deflection, which means greater isolation efficiency. We have these small springs here, and the difference with springs compared to neoprene is they give you typically a higher deflection, greater isolation efficiency, but they also don't have any damping. What that means is they're not trying to stop the movement, and so they move more freely, and their isolation efficiency, even if the spring had the same deflection as some neoprene mount, the spring isolator will outperform it. So we get our 4 springs here. Now we're getting a little bit more serious and maybe actually solving our problem. Let's see what we get. And you'll notice right away, when I put this imbalanced fan down on our springs, you can see that it drops down, it squashes. We're getting some deflection now. Probably not a whole lot, maybe a 1/4 inch, but we're getting some. So let's see what the difference is now. At high speed, it actually is pretty good. I can still feel the vibration in the table, but it's reduced it significantly. I don't have to hang on to it. I don't have isolators trying to escape. Now it's working fairly well. As we drop that frequency, the isolation efficiency slowly drops as well, because we're approaching the natural frequency of the spring. Let's see if we can find it. Now we're getting pretty close, and that's why it's allowing for all this movement. And once you get to the natural frequency of the spring, it actually makes your situation worse than had you just mounted it direct to the floor. So it's something you definitely want to avoid. The typical rule of thumb for vibration isolation is that the natural frequency of your isolator should be no more than a third that of your disturbing frequency of your piece of equipment. So if you had a unit, that's rotating at 1200 RPM, you would want an isolator that has a natural frequency at about 400 RPM. So in this case, it definitely worked fairly well at the higher frequencies, but you can see the lower we got, the less the isolation efficiency was. So if we wanted to run this thing at a lower frequency, what we need is a spring with even higher deflection. And springs, you can get them, typically the standard ones will be in 1 or maybe 2 inch, but they come in 3, 4, 5 inch, depending on the type of equipment you're using. Of course, you can see it's bigger, so the greater the deflection of spring you're using, the bigger it's going to be. So it can often be hard to isolate low RPM equipment if it's really small. So we've got these big springs here, and we're going to move those into place. They have a better deflection than our red ones. So when we put the weight on it, it will drop more. That's the deflection. That's the natural frequency of this system. And so when we turn this on to high, much less vibration in the cable. I can still feel it, but quite a bit less than what it was before. So you're getting a pretty good vibration isolation. If this thing wasn't so imbalanced, you'd probably take it out almost completely. So as we drop that speed though, we're still going to drop the isolation efficiency and come closer and closer to the natural frequency of these springs. Let's see if I can find it with these ones. Now you can see I'm getting close now, but I've had to go quite a bit lower. Almost to the point where this thing stops. Now we're pretty much at the natural frequency, and it's bouncing all over the place. And this is the situation you want to avoid. But of course, if you look at this fan, it's barely moving at all. It's a very low frequency that we've set it to. But judging by the deflection, we're maybe getting close to ½ an inch at best. So it's still not a whole lot of deflection for what we're doing here. Like say you're going to want something higher than that. When you get your data sheets from your manufacturers, you'll find that the rated deflection's on there. So you think, okay, well I'm getting an inch, and we can work that out and figure out your isolation efficiency. But you actually need to look at the actual deflection. That's the amount, when you put the weight on there, then it actually drops down. The rated deflection is only for if you happen to load that isolator right to its maximum capacity, which isn't very common. So usually a 1 inch isolator, you're going to get maybe 70 to 80% of that, of isolation or of your deflection and your isolation efficiency. It's something to keep in mind. And so that's basically how deflection, how the frequency, the disturbing frequency of your equipment all come together, and why you've got to really pay attention to it when you're selecting isolators for your equipment. Thank you very much.